Have you ever just stopped and wondered how your computer can sift through gigabytes of information, or how your phone pulls up one single contact from thousands in literally the blink of an eye? I mean, it really does feel like magic, but it's not. It's actually one of the most elegant and powerful ideas in all of computer science. So today, we're going to pull back that curtain and see exactly how this digital magic trick works. Let's dive in.
Seriously, just think about it for a second. You type 1 or 2 letters into your Contacts app, and boom, the right name just pops up. There's no waiting, no loading bar, nothing. How on earth is that possible? It can't be searching through every single contact one by one, right? That would take forever. So what's the secret? Well, to solve this little mystery, we have to understand the problem at its core.
So here's our game plan. First, we're going to define what this data lookup problem really is. Then we'll check out the simple, kind of obvious ways to solve it and see why they just don't cut it. After that, we get to the good stuff, the breakthrough idea of hashing. We'll even tackle its one big complication, and finally, wrap our heads around the art of the trade-off that makes our digital world spin.
Okay, so at its heart, almost every database, every contact list, every storage system out there is trying to solve the exact same problem. It's all about connecting one piece of information to another.
In the world of computer science, we have this abstract concept called a dictionary. And all it is really is a way to think about systems that store info as key-value pairs. The key is that one unique thing you use to look something up. So for a bank, your account number is the key. The value? Well, that's everything else. Your name, your balance, all your transactions. You give the system the key, and it gives you back the value. Simple as that.
So any of these dictionaries needs a few basic tools in its toolkit. You've got to be able to find something with its key, of course. You need to be able to insert a new thing, and you need to be able to remove an old one. These are the core actions, and the whole goal is to make them happen as fast as humanly or, well, digitally possible.
All right, so if you were building a system like this from the ground up, how would you do it? Well, the most obvious ideas are usually the simplest, but as we're about to see, they come with a pretty big catch.
So your first 2 instincts would probably be to just use a list, right? On one hand, you could have an unordered list. You just chuck new data onto the end whenever it comes in. Super easy to add stuff, but finding something? Oh, that's a nightmare. You have to check every single item, one by one from the very beginning. So, on the other hand, you could keep the list sorted. Now, finding things is way faster. But adding a new item, that becomes a huge pain, because you have to find the perfect spot and then shift everything else over to make room. Ugh!
So how do we speed up that search in a sorted list? We use this really clever trick called binary search. Instead of starting at the beginning, you jump straight to the middle of the list. Then you just ask, is the contact I'm looking for before or after this point? And whatever the answer is, you can instantly just throw away half the list. You just keep doing that. Jump to the middle of what's left, cut it in half, again and again. You narrow it down incredibly fast.
And this right here, this table sums up our whole problem. We're stuck in this trade-off. An unordered list gives us lightning-fast inserts but painfully slow searches. An ordered list with that binary search trick gives us fast searches, but now adding new data is slow. It feels like we have to choose fast searches or fast updates. We can't have both, or can we?
This is where computer scientists got really clever. They took a step back and realized, hey, maybe the goal isn't just to make searching faster. Maybe the real goal is to get rid of searching altogether.
I mean, think about that question. It's a total game changer. What if instead of having to look for our data, we could just know where it is? What if we could just calculate its exact location instantly?
And the answer to that question is something called a hash function. Honestly, you can think of it like a perfect filing clerk. You hand it a key, say a phone number, and it doesn't go searching through drawers. It does a super quick calculation in its head and immediately tells you, oh, that file, it's in cabinet 42, drawer 3. It directly converts your key into a physical address. No searching required.
Here's a really simple way to imagine how that calculation works. Let's say we have 100 storage slots, numbered 0 to 99. We can take a key, like a really long phone number, and just do some simple math. Divide it by 100 and take the remainder. So a phone number ending in 04 gets assigned to slot number 4. A number ending in 89 goes straight to slot 89. It's a direct, totally repeatable calculation that just gives us an address. Instantly. This direct lookup gets us to what's known in computer science as O of 1, or constant time. And let me tell you, this is the Holy Grail. It means that the operation takes the exact same tiny amount of time whether you have 10 contacts or 10 million. It literally does not get any faster than this.
Of course, it all sounds a little too perfect, right? A little too good to be true. And yeah, there is one pretty big catch we have to figure out.
Okay, so let's go back to our simple phone number example. What happens if we get two different phone numbers that both happen to end in the number 89? Our little hash function would tell us to put both of them in the same exact slot, slot 89. Uh-oh, now we have a problem.
This is what we call a collision, and it's pretty much unavoidable when you're trying to map a huge universe of possible keys, like every phone number in the world, into a much smaller set of storage slots. So how do we deal with this without slowing the whole system down?
Well, the most common solution is actually really simple and elegant. It's called chaining. The idea is, instead of storing just one item in each slot, we store a little list. So, when a collision happens, and two items want to go to the same spot, no problem. We just add the new item to the little list that's already there. The hash function still gets us to the right tiny neighborhood in an instant, and then we just have to do a quick search through a super short list of maybe 2 or 3 items. It keeps the whole thing incredibly fast.
So let's bring this all together and see exactly why this idea of hashing is just so unbelievably powerful.
And this table really says it all. While those simple lists forced us to choose between fast updates or fast searches, the hash table just comes in and gives us the best of both worlds. On average, searching, inserting, and deleting are all constant time, O of 1 operations. This is it. This is why hash tables, the data structure built on this idea, are used absolutely everywhere in modern computing.
Now, the secret to keeping it that fast is managing something called the load factor. It's just a simple ratio. How many items do you have divided by how many storage slots are available? As long as you keep this ratio low, say by automatically making the table bigger if it gets too full, you basically guarantee that those little collision chains stay short and your O1 performance stays rock solid.
But as this quote from our source material really points out, the real magic, the secret sauce, is in picking the right hash function. A good one will spread all the keys out nice and evenly, keeping collisions to a minimum. A bad one can cause everything to clump together, turning your super fast hash table right back into a slow, plunky list. It really does take a deep understanding of the kind of data you're working with.
So, the next time your phone finds a contact instantly, you'll know it's not magic. It's the result of a truly brilliant solution to a fundamental problem. A careful balancing act between simplicity, speed, and power. And it leaves us with one final thought. As the amount of data in our world continues to just explode, how will we keep innovating on these trade-offs to build the tools of tomorrow that aren't just powerful, but feel truly instantaneous?